Welcome to the Deep Dive. Today we are taking on, one of the biggest misconceptions in 20th century physics history, really.
Yeah, this idea that Albert Einstein was just sort of a grumpy old traditionalist.
Exactly. That he rejected quantum theory simply because he couldn't handle the weirdness. You know the story, him waving his hands about God not playing dice, getting left behind by the youngsters.
Right. And that picture, it just fundamentally misrepresents his actual role. Our sources, which really offer a deep reappraisal of his decades-long struggle with the theory, they show something quite different.
Which is?
That he wasn't just some sideline critic. He was absolutely essential to the birth of quantum mechanics. And later, yeah, he became its most important, probably its most insightful adversary.
So that's our mission today. We're going to try and reposition Einstein. Not as this figure of failure, but maybe more like an engine of progress.
That's a good way to put it. His relentless questioning, his kind of open-minded skepticism, that friction point ultimately generated the concepts, the groundwork for some of the hottest areas in modern physics.
Like quantum information theory, QIT.
Exactly. QIT is a huge one that stems directly from the questions he raised.
And if we sort of boil down that entire decades-long struggle, what's the philosophical fault line?
It really comes down to realism. Einstein was just convinced that physics must be rooted in deterministic realism, meaning that physical things like momentum, position, they have definite values that exist before you measure them, whether or not we choose to look.
Okay.
And that a complete theory should, describe that underlying reality completely. He wanted certainty, which is why he famously told Max Born that, the old one, meaning God, is not playing at dice.
Okay, right. But let's start with maybe the startling reminder of just how much he was playing dice, or at least setting up the game in the early days. He wasn't just a participant in the quantum revolution. You're saying he basically fired the starting pistol.
Absolutely. We really need to look back at his contributions, say, between 1905 and the early 1920s. Everyone knows Max Planck, right? Introduced the idea of the energy element, 4H dollar.
As a mathematical trick, wasn't it? To solve the black body radiation problem.
Pretty much, yeah. But it was Einstein in 1905 who first really grasped that this wasn't just math. It represented a physical energy discontinuity, a real discrete packet of light energy.
A photon.
The photon. That was arguably the moment quantum theory became a physical reality, not just a calculation tool.
And what's often missed, I think, is the depth of that 1905 insight. Most pop accounts credit the photoelectric effect, right?
Yeah, that's the standard story.
But the sources we looked at emphasize his deduction about the particle-like nature of light. It actually came from analyzing the entropy of radiation using Wien's law.
Which is a much deeper thermodynamic argument. It shows he wasn't just looking at one effect. He was thinking about the fundamental nature of energy and statistics, an incredibly deep understanding.
And he didn't stop there. He immediately took this quantum idea, this discontinuity, and applied it elsewhere.
Right away. He used it to solve a major puzzle in thermodynamics, the specific heat of solids. Classical physics had this law, Dulong and Petit's law, that said the specific heat of elements should be constant.
But it wasn't always, right? Like diamond.
Exactly. Diamond, for example, completely failed to follow this rule at normal temperatures. Big mystery. Einstein applied his quantization idea to the vibrations of the atoms in the solid, and suddenly, boom, the anomaly vanished. It just worked.
He sounds like a real radical innovator back then.
Totally. Which makes what comes next so interesting, because in a way, he sets the trap for his future self.
How so?
Well, in 1916, he publishes this landmark paper on spontaneous and stimulated emission.
Nice.
This is super critical because it connects Planck's radiation law directly to Niels Bohr's model of atomic transitions. He introduced his famous A and B coefficients.
The A and B coefficients. Stimulated emission is the basis for lasers, isn't it?
It is. But the crucial part for this story is the A coefficient for spontaneous emission. To make the theory match experiments, Einstein had to describe quantum jumps, an atom spitting out a photon, as fundamentally chance events.
Probabilistic.
Inherently probabilistic. The theory itself, as formulated by him, had randomness baked in from that point.
Wow. So the man who gave us the math for quantum chance spent the next 40 years arguing against the reality of that chance.
That's the irony, yes. And beyond his own huge theoretical work, he was also actively encouraging the next generation, wasn't he?
He was. He gave crucial advice to Werner Heisenberg when Heisenberg was struggling to formulate the uncertainty principle.
Sort of nudging him in the right direction.
Yeah. And he was a major supporter of Louis de Broglie's really audacious hypothesis, the idea that particles, like electrons, could also behave like waves.
Which was way out there at the time, so he's mentoring the very people who would develop the interpretation of quantum mechanics he'd later fight so strongly against.
Which kind of brings us neatly to the big split, the philosophical divide.
Yeah.
By about 1927, the arguments weren't just about the math anymore, were they?
No, not at all. It became about what physics is, fundamentally, what its goals are. And Einstein's own philosophical foundation had shifted quite dramatically.
Right. Let's unpack that shift, because it's really key to understanding why he couldn't get on board with the Copenhagen view. Early Einstein, influenced by Ernst Mach.
Yeah, the philosopher Ernst Mach. Mach was big on positivism.
Define positivism for us quickly.
Basically, the idea that concepts, like say time or space, are only meaningful if you can define them through a measurement, at least in principle. If you can't measure it, it's not physics.
And that skepticism helped him create special relativity.
Absolutely. By ditching absolute space and absolute time, things you couldn't observe or measure, he was able to build relativity. Pure Machian thinking, in a way.
But then he changed his mind.
He did. Our sources show that by about 1921, he had moved away from that strict positivism. He started arguing that actually theory comes first. Theory tells you what you can observe, not the other way around.
Okay, a reversal.
A big one. And he solidified his belief in what he called classical realism, or sometimes macro-realism. It rests on two main ideas.
Okay, what are they?
First, physical properties, things like momentum, position, spin. They have definite values before you measure them, and regardless of whether you measure them, the moon is there even when nobody looks.
Right, realism. And second?
Second, measurement ideally should be non-invasive. It shouldn't fundamentally change the value that was already there. It just reveals it.
And this whole view is just completely opposed to the Copenhagen interpretation.
Diametrically opposed, yes. Bohr and Heisenberg announced their view around 1927, and it pretty quickly became the orthodox way to think about quantum mechanics.
And their view was?
They argued that quantum theory isn't really about describing some underlying hidden reality. It's only concerned with predicting the results of experiments. Reproducible statistical results.
Okay, so if Einstein thinks properties are definite and real before measurement, what did Bohr and Heisenberg think about the central object in the theory, the wave function? Fancy day.
Ah, good question. They said Canty eyes is objective. Yes, it's part of the physics. But, crucially, it's not real in Einstein's sense. It doesn't describe what is.
What does it describe then?
It represents a potential, a tendency. Heisenberg used the term potentia. It gives you the probabilities for different outcomes if you were to make a measurement.
So, back to your coin analogy from before we started. For Einstein, the hidden coin is already heads or tails.
Right. Definite state, just unknown to us.
But for Bohr and Heisenberg?
For them, before you look, the coin is genuinely both heads and tails simultaneously, represented by the wave function. It's only the act of observation, the measurement, that forces it to collapse into one definite state, heads or tails.
Okay, I see the clash. And the practical result of this Copenhagen approach was this thing called the measurement problem, wasn't it?
Yes, exactly. How do you get from this weird quantum world of probabilities and superpositions, described by Tassi, to the definite classical world we actually experience?
Where coins are definitely heads or tails, not both.
Right. To handle that transition, Bohr and Heisenberg basically had to introduce what they called a Heisenberg cut.
A cut, like a dividing line.
Sort of, yeah, a conceptual dividing line. You arbitrarily decide where the quantum system ends and the classical measuring apparatus begins.
Arbitrarily.
Pretty much. Below the cut, things obey the weird quantum rules, the probabilistic wave equation.
Yeah.
Above the cut, the detector, the observer, the cat in Schrodinger's box things are assumed to be classical and definite.
Wait a minute. But the measuring apparatus, even a Geiger counter or a physicist's eye, it's made of atoms, isn't it? Shouldn't it also obey quantum mechanics?
Ah, you've hit precisely Einstein's objection. That's exactly what he couldn't accept.
It seems inconsistent.
He thought so too. He believed quantum mechanics, if it was a fundamental theory, should be universal. It should apply to everything, the electron, the detector, the observer, the entire universe. This cut seemed like an artificial and intellectually unsatisfying patch, a sign the theory wasn't telling the whole story.
It pointed towards incompleteness.
For Einstein, yes. It strongly suggested the theory was incomplete. Which brings us then to his big strategic counterattack in 1935.
The EPR paper. Einstein, Podolsky, and Rosen.
That's the one. A logical assault designed not just to poke holes, but to prove logically, mathematically, that quantum mechanics, as it stood, had to be incomplete.
Okay, what was the core logic? It's famously tricky?
It is, but the structure is actually quite elegant, quite simple in its way. EPR set out to show that you cannot simultaneously believe two things are true.
Okay.
Proposition A1. Quantum theory is complete, meaning the wave function tells you everything there is to know about the system's reality. And Proposition A2. Quantum theory is local.
Meaning no spooky action at a distance. Nothing travels faster than light, and events here can't instantly affect things way over there.
Exactly. Locality. So EPR argued, you can't hold both A1, completeness, and A2, locality, to be true based on their thought experiment. One of them must be false.
And since Einstein deeply believed in both completeness and locality,
He concluded that A1 must be the false one. Quantum mechanics had to be incomplete. There must be some missing information, some hidden variables that the wave function wasn't capturing, which would restore both locality and determinism.
right, can we make this concrete? The thought experiment itself?
Yeah.
Maybe the later version with the boxes.
Yeah, the boxes version, which Einstein discussed even earlier, maybe makes it more visceral. Imagine you prepare two particles. They're linked in some special quantum way entangled. Let's say they're guaranteed to have opposite spins, but you don't know which is which yet.
Okay, linked but uncertain.
Right. Put them in a box, divide the box, send one half to Paris, the other half instantly, magically, to Tokyo, thousands of kilometers apart.
Okay, got it. Paris and Tokyo.
Oh, now, according to quantum mechanics, before anyone measures, each particle is in a superposition sort of spin up and spin down at the same time, but their fates are linked. If Paris finds spin up, Tokyo must be spin down, and vice versa.
Right, they're correlated.
So the observer in Paris opens their box, measures the particle, and finds its spin up.
Okay.
According to the standard quantum formalism, at that exact instant, the wave function describing the particle way over in Tokyo instantaneously collapses. It's forced into the definite state spin down.
Instantaneously.
Okay.
Across 10,000 kilometers.
That's what the math says. The information that Tokyo's particle is now definitely spin down seems to have traveled instantly. This is the spooky action at a distance, Spukhaftfernwirkung, that Einstein found so unacceptable.
It seems to violate relativity, the idea that nothing travels faster than light.
It certainly looks like it does. Now, in the famous Solvay debates, Bohr managed to kind of deflect Einstein's attacks, right? Even though this EPR argument seems like a killer blow, how did Bohr get around it?
Yeah, Bohr's response was notoriously subtle. And hard to pin down sometimes.
It was. But effectively, Bohr argued that you couldn't separate the quantum particles from the entire measurement setup, including the classical measuring devices in Paris and Tokyo. The whole thing forms an indivisible whole.
Okay.
And the very act of measuring the particle in Paris, which requires interacting with a classical device, necessarily disturbs the system in a way that prevents you from using the instantaneous correlation to send a useful message faster than light.
So while the correlation might be instantaneous, you can't use it to signal. Like Paris can't decide to send a 1 or a 0 to Tokyo instantly by choosing what to measure.
Exactly. No actual information transfer faster than light. So technically, no violation of relativity's core principle about causality. It preserved the formalism, but it didn't really satisfy Einstein's demand for a local, realistic underlying story.
So Bohr kind of won the debate in the sense that the physics community mostly moved on, except in Copenhagen.
Largely, yes. Einstein's criticisms were often seen as, him being stuck in the past. His views were marginalized for a long time.
But as you said earlier, his critique brought out these profoundly disturbing features. He knew where the conceptual weak spots were.
He absolutely did. And this is where this story takes a fascinating turn, leaping forward decades from philosophy right back into cutting-edge physics. This brings us to the vindication.
Vindication.
In a sense, yeah. For about 30 years, the EPR paper was treated mostly as a philosophical puzzle. Interesting, but maybe not real physics you could test.
Until John Bell came along in the 1960s.
Right. John Bell, a physicist at CERN, who actually described himself as a follower of Einstein's thinking on this. He showed that the questions EPR raised, locality versus completeness, weren't just philosophy, they had experimentally testable consequences.
This is Bell's theorem.
Bell's theorem. It was a bombshell. Bell proved mathematically that any theory based on Einstein's preferred worldview, that is, local realism, hidden variables that obey locality, makes statistical predictions that are inherently different from the predictions of standard quantum mechanics.
Wait, so he found a way to actually test Einstein's hidden variables idea against standard quantum mechanics.
Precisely. He quantified the disagreement. He derived what are now called Bell inequalities. If local realism is true, the results of certain experiments involving entangled particles must obey these inequalities. If quantum mechanics is true, these inequalities should be violated.
So it became an experimental question. What did the experiments show?
Starting with a lane aspect in the early 80s, and many, many times since, with increasing precision, the experiments have overwhelmingly shown that Bell's inequalities are violated,
They're violated.
just as standard quantum mechanics predicts.
So what does that mean? If the experiments confirm quantum mechanics over Bell's inequalities.
It means we have to give up something fundamental from Einstein's worldview. If the quantum mechanical predictions are right, you cannot have both locality and realism. You have to choose. Given the strong correlations observed, most physicists conclude we have to give up locality. Nature is non-local. That spooky action is, in some sense, real.
Wow. Okay. So Einstein's attempt to prove quantum mechanics incomplete actually led to proof that the world is weirder than he thought.
In a profound way, yes. And here's where the critique stops being just history and becomes the absolute foundation of modern quantum technologies.
Quantum information theory.
QIT. This realization that entanglement, the very spooky action Einstein hated, is a real, controllable, measurable phenomenon that wasn't a paradox to be explained away anymore. It became a resource.
The bug became a feature.
The bug became the most powerful feature we know. Think about quantum computing. Key ideas are built directly on these Einstein-highlighted weirdnesses.
Like quantum parallelism, using superposition, the particle being in multiple states at once to do many calculations simultaneously.
Exactly, that's the superposition part. And then you link these superposed states using entanglement. There's a common quantum logic gate called the CNOT gate, controlled not to.
What does that do?
It flips the state of one quantum bit, one qubit, only if another control qubit is in a certain state. Doing this is a primary way to create these EPR-like entangled states on demand in a quantum computer,
Linking the fates of qubits.
linking them non-locally. This ability to create and manipulate these correlations is what gives quantum computers their theoretical power for certain problems.
It's not just computing, right? Quantum cryptography, too.
Absolutely. Some of the most famous quantum cryptography protocols, like the Eckert protocol from 1991, explicitly use entangled EPR pairs. Security is guaranteed by testing Bell's inequalities, checking for the quantum correlations Einstein found spoopy.
So the spookiness guarantees the security.
In that protocol, yes. And even simpler quantum key distribution relies on related quantum features, like the no-cloning theorem. Another fundamental quantum rule. It says you cannot make a perfect copy of an unknown arbitrary quantum state. You just can't.
How does that help security?
Well, if an eavesdropper, call her Eve, tries to intercept a quantum key being sent, say, encoded in single photons, and measure it to copy it, the very act of measuring will generally disturb the photon's state.
Changing the message.
Exactly. It leaves detectable errors, revealing her presence. You can't just passively copy the quantum information without a trace. It's physically impossible.
So, stepping back,
Mm-hmm.
it really sounds like it was Einstein's constant pressure, his demand for clarity and physical realism, that forced physicists to really grapple with these deep, weird features of quantum mechanics.
I think that's fair to say. The standard Copenhagen view, while practical for calculation, our sources suggest it might have actually stifled novelty along with criticism and discussion. It sort of said, shut up and calculate.
Don't ask what it means, just use the rules.
Right. Whereas Einstein's approach, this open-minded, questioning, pragmatic approach, even though he was ultimately wrong about local realism, it was much more favorable to generating fundamentally new ideas.
Like Bell's theorem and everything that flowed from it.
Bell's theorem, QIT. His relentless demand for a consistent, coherent picture forced the theory to reveal its most profound and ultimately most useful secrets. His greatest legacy might just be how productively wrong he was.
He made the theory stronger by refusing to just accept it.
Naively put.
Okay, so that brings us to our final thought for you, the listener. Even after Bell's theorem showed that nature seems to prefer non-locality over local realism, Einstein probably wouldn't have just given up, would he?
Unlikely. His ultimate goal was always grander. He wanted a deeper theory, a unified field theory, probably found from without, a completely new foundation that would explain quantum mechanics as an approximation, rather than just tinkering with quantum theory from within.
So this raises a really fascinating question. We know the choice was effectively between realism and locality. Nature, via Bell experiments, seems to choose non-locality. If Einstein were alive today, knowing this, what kind of theory might he have found palatable?
That's the million-dollar question, isn't it? Would he have maybe finally embraced a non-local realist theory? Something like David Bohm's pilot wave model, which has real particles guided by a non-local wave function. It keeps realism, but sacrifices locality.
Or maybe something even more radical, like spontaneous collapse theories.
Yeah, theories like GRW that actually change the rules of quantum mechanics itself, they suggest the wave function collapses randomly on its own, even without measurement, thus solving the measurement problem and restoring a kind of macro-realism, but altering the fundamental dynamics.
We'll never know, of course.
Mm,
But it's a testament to his deep thinking that the questions he raised are still driving these debates today.
absolutely. It remains one of physics' great ongoing discussions, spurred almost entirely by his decades of brilliant, uncompromising dissent.